In this video, we're going to talk about horizontal asymptotes, or limits as x approaches positive or negative infinity. So here we're talking about the end behavior of a function, what happens to the output of the function as the input gets arbitrarily large or arbitrarily large in the negative direction. So the definition is that the limit as x approaches infinity of f of x is equal to L if, as x gets larger, f of x gets arbitrarily close to L. So we would write that as the limit as x approaches infinity, as x gets large, of f of x is equal to L. Similarly, we could define the limit as x approaches negative infinity of f of x, and that could be equal to the same value L, or it could be equal to some different value k. A classic example where the limit of the function as f of x approaches positive or negative infinity is a finite number would be f of x equals 1 over x. So we've graphed the function 1 over x before. F of x equals 1 over x is looking like this. We already know that there's a vertical asymptote at x equals 0, but as x approaches infinity, 1 over x is getting arbitrarily small. So 1 over x gets close to 0 as x approaches infinity, and also as x approaches negative infinity. As we plug in small values for x, as we plug in large values for x, 1 over x gets smaller and smaller and smaller. So this is limit as x goes to infinity of 1 over x equals 0, and limit as x goes to negative infinity of 1 over x is also equal to 0. The end behavior of the function in both directions, the function is heading, the output of the function is going towards 0. In a situation like that, where the limit of the function as x goes to positive or negative infinity is a constant number, we say that the function f of x has a horizontal asymptote. So f of x has a horizontal asymptote at the value y equals L if the limit as x approaches positive infinity of f of x is equal to L, or the limit as x goes to negative infinity of f of x equals L, or both. And it could be the case that, as in the situation above, the limit as x approaches infinity and negative infinity is the same for f of x, or it could be going to towards two different values. So let's look at an example together. We want to determine whether the following function has horizontal asymptotes. And for this, like I said, we want to look at the limit as x goes towards infinity of the function 5x squared plus 2x over 6x squared plus 10. So a sort of a trick for dealing with these kinds of infinite limits is that, we see that the top is going towards infinity, the bottom is going towards infinity. That doesn't help us a whole lot. So what we're going to do instead is multiply both the numerator and the denominator by 1 over the highest power of x. So this is the limit as x goes towards infinity of 5x squared plus 2x divided by 6x squared plus 10. And we're going to multiply the numerator and the denominator by the same thing, by the highest power of x in the denominator. So 1 over x squared, 1 over x squared. And when we do that, now we've got the limit as x goes to infinity of 5x squared over x squared, distributing that 1 over x squared, plus 2x over x squared divided by 6x squared over x squared plus 10 over x squared. So let's sort of simplify that. That's the limit as x goes to infinity of now the x squareds will cancel here, and one of these x's will cancel with one of those x's. So our our numerator becomes 5 plus 2 over x divided by, and similarly on the bottom, the x squareds are going to cancel out of the first term, so that's 6 plus 10 over x squared, nothing cancels there. And now let's think about what happens to each of those terms. Well, as x goes towards infinity, 5 just continues being 5, it doesn't care. What happens to 2 over x? That's 2 over a really big number, 2 over like a million, that's getting closer and closer to 0. What happens to 6? 6 keeps just hanging out being 6. And what happens to 10 over x squared? That's 10 over a really large number squared. That's going to 10 over something really big. That's getting closer and closer and closer to 0. So what happens to the entire limit? The entire limit approaches 5/6. And if we looked at the limit as x approached negative infinity of this quantity, 5x squared plus 2x over 6x squared plus 10, we could do the exact same process and find that, again, the numerator went to 5 and the denominator went to 6, because if x is going to a negative large number, if x is going towards negative infinity, 2 over x is still going towards 0, and similarly 10 over x squared is still going towards 0. So this limit would also be 5 over 6. And because the limit as x approaches positive or negative infinity of our function f of x is a constant L, so this is a real number, not plus or minus infinity, that tells us that there is a horizontal asymptote at the line y equals 5/6. So y equals 5/6 is a horizontal asymptote because the limit as x goes to positive or negative infinity of f of x is 5/6. If you graph this function on your calculator, you'll see something that looks kind of like this. There's a horizontal asymptote at 5/6, so just below 1. And this particular function, is going to look something like this. It's going towards 5/6 from below, but never quite hitting it. Later on, we'll do curve sketching, and we'll have a better idea of how to graph these functions in general in more detail. But for now, we've just got a horizontal asymptote at y equals 5/6. So I'd like you to try to figure out whether the following functions have horizontal asymptotes, and find the limits as x goes to infinity for each of the following functions. You can still use that trick of multiplying the numerator and denominator by 1 over x to the n, where n is the largest power of x in the denominator. So we can do that, just like the problem above. But I'd also like you to think about, as you're working on these, as you're trying to find solutions for each of these, is there an even better shortcut for finding these limits as x goes to infinity for these rational functions? So try these and keep that idea of hunting for a shortcut in mind. Pause the video and try these out. We'll talk about them in just a moment. Okay, for this first example, we're looking for horizontal asymptotes. So we're looking at the limit as x goes towards positive infinity of this function, x to the third plus 3x squared over 4x cubed minus 100. And so we are going to do that same trick of multiplying the top and the bottom by 1 over x cubed, because the third power is the highest power in the denominator. So that's going to give us a limit as x goes towards infinity of x cubed over x cubed, distributing the 1 over x cubed through, plus 3x squared over x cubed divided by 4x cubed over x cubed minus 100 over x cubed. So now let's simplify. That's the limit as x goes to infinity of x cubed over x cubed is just 1. 3x squared over x cubed is 3 over x. 4x cubed over x cubed is just 4. Minus 100 over x cubed is still just 100 over x cubed. And now let's think about what happens to each of those terms as x goes to infinity. So as x gets infinitely large, 1 just stays as 1. 3 over x, 3 over an infinitely large number, it just is going towards 0. 4 is going towards 4. And 100 over a really big number cubed is going towards 0. So this entire term is just going towards 1 plus 0 over 4 minus 0. It's going to 1/4. And so that so that tells us that there is a horizontal asymptote at y equals 1/4. So a line across at y equals 1/4, where the function is approaching 1/4 as x goes towards positive infinity. Notice if you put in the limit as x goes towards negative infinity, it would still be, the limit as x goes towards negative infinity of 1 plus 3 over x divided by 4 minus 100 over x cubed. And that would still go to 1/4 as well. So the end behavior in both directions, the function is going towards 1/4. Okay, let's look at our next function. So again, we're looking at the limit as x goes towards infinity of our function 10x to the 5th plus 8 divided by x to the 6th minus 7x. And we're going to use that same method again of dividing the top and the bottom by the highest power in the denominator. And that will give us the limit as x goes towards infinity of 10x to the 5th over x to the 6th plus 8 over x to the 6th divided by x to the 6th over x to the 6th minus 7x over x to the 6th. And if we simplify that, we've got the limit as x goes towards infinity of 10 over x is the first term simplified, plus 8 over x to the 6th divided by x to the 6th over x to the 6th is 1, minus 7 over x to the 5th. And as x goes towards infinity, 10 over x goes towards 0, 8 over x to the 6th goes towards 0, 1 goes towards 1, and 7 over x to the 5th goes toward 0. So what is this entire thing doing? This is going towards 0 over 1, which is equal to 0. And similarly, the limit as x goes towards negative infinity of 10x to the 5th plus 8 over x to the 6th minus 7x would also be equal to 0. So we do have a horizontal asymptote at y equals 0. All right, let's take a look at our last example. Limit as x goes towards infinity of negative x to the 4th plus 5x divided by 3x squared minus 2x. We're dividing the numerator and the denominator by the highest power in the denominator. And so we've got the limit as x goes towards infinity of negative x to the 4th over x squared plus 5x over x squared divided by 3x squared over x squared minus 2x over x squared. And so that's the limit as x goes towards infinity of negative x squared is what the first term reduces to, plus 5 over x divided by 3 minus 2 over x. So what happens to each of those terms? So 3 continues being 3, 2 over x goes towards 0, 5 over x goes towards 0, negative x squared. As x goes towards infinity, the whole term negative x squared is going towards negative infinity. So the limit of this function is negative infinity as x approaches infinity. We could also look at what happens as x approaches negative infinity. So the same reductions that we did, the algebra we did, is still valid. So this would reduce to negative x squared plus 5 over x divided by 3 minus 2 over x. And as x approaches negative infinity, well, this is still going towards 0, this is still going towards 0, this is still going towards 3, and we've got negative x squared. So the negative infinity, or negative big number squared, is going to become a negative squared is a positive. So this is going towards infinity, but there's a negative still sitting in front of it. So it's still going towards negative infinity. So we're going towards, negative infinity over 3, which is still negative infinity. So because the limit as x goes to infinity is not a finite number, neither the limit as x goes towards infinity or the limit as x goes towards negative infinity, that is not finite. That means that there is no horizontal asymptote for the function that we've just been talking about, for this function negative x to the fourth plus 5x divided by 3x squared minus 2x. So I asked you to think about whether there might be a shortcut for thinking about the limits as x goes to infinity for rational functions. Let's just summarize what we saw before. So when we looked at the first example, x cubed plus 3x squared over 4x cubed minus 100, we saw that this goes to 1/4 as x goes to infinity, and also as x goes towards negative infinity. For the function g of x, we saw that this function went towards 0 as x goes towards infinity, and also as x went towards negative infinity. And for our last function, we saw that this went to negative infinity as x goes to infinity, and in this case also as x goes to negative infinity. So any guesses about a pattern here? I'm going to pause one more time and let you think about it. Okay, so basically what determines the end behavior of a function, of a rational function, a polynomial over a polynomial. And when I say end behavior, what I mean by that is the limit as x goes towards positive or negative infinity of p of x over q of x, some rational function. What is the main thing guiding that? It's going to be the largest powers of x in the numerator and denominator. So here in the first example, we see that the largest powers of x are x to the third, and these are equal largest powers. And anytime that happens, the limit as x goes to positive or negative infinity is going to be the ratio of the coefficients of those largest powers. So anytime the largest power in the numerator and denominator are equal, the limit as x goes towards infinity of that p of x over q of x is going to be equal to the ratio of the coefficient of leading power in the numerator divided by the coefficient of the leading power, in other words, the largest exponent of x, there was a 1 in front of this, so 1 is the coefficient there, and there's a 4 in front of that, so 4 in front of that. So it's the ratio of the coefficients if they have equal largest powers. If the leading power in the numerator is less than the leading power in the denominator, then this is going to always go to 0 because as x is going towards infinity, the highest power basically wins. So this is getting big faster than that is getting big. And so therefore, since the denominator is getting towards infinity faster than the numerator, the whole thing is going to go towards 0. And anytime that the power in the numerator is larger than the largest power in the denominator, so here 4 and 2, the highest power in the numerator was larger, then we are going to go either to positive infinity or negative infinity depending on the situation. Here we went to negative infinity, but there are other examples where we would go towards negative infinity, towards positive infinity. So to summarize our shortcut for rational functions of the form p of x over q of x, that's a polynomial divided by a polynomial, we just need to look at the highest power in the numerator and the denominator. If the highest powers are equal, then the limit as x goes to infinity, to plus or minus infinity, of f of x is the ratio of the leading coefficients. If the highest power in the denominator is larger, then the limit as x goes to positive or negative infinity of f of x is 0. And if the highest power in the numerator is larger, the top is going faster to positive or negative infinity, then the limit as x goes to plus or minus infinity of the function is going to be plus or minus infinity.